Preparations for field operations begin with the acquisition and outfitting of a suitable vessel. The motor vessel Virgo out of Houston, Texas was chosen for use during the Aleutian experiment. A 25 by 45-foot engineering laboratory was placed on the deck to house the ocean bottom seismographs, and a 17-ton hydraulic crane was welded to the back deck. All ocean bottom seismograph units and project auxiliary equipment must be thoroughly cleaned and checked out prior to installation on the ship. Equipment involved with ocean bottom seismograph setup and maintenance, unit recall and recovery, timing, navigation, communications, and hydroacoustic wave recording must be installed into an intricate network for smooth, efficient sea operation. The shipboard hydraulic crane is used not only for loading and unloading of equipment, but also for ocean bottom seismograph deployment and recovery, and for movement of any large calibration explosives used during field operations. A 350-pound expendable anchor, shown here, is used to sink the ocean bottom seismograph to the ocean floor. The weight of a complete unit is 1,780 pounds in air, or 250 pounds in water. After release from the anchor at recall, the unit has a buoyancy of 100 pounds. The Texas Instruments ocean bottom seismograph is a self-contained, free-fall, remote recall, deep ocean instrument package. The unit is designed to operate unattended and untethered in ocean depths up to 25,000 feet, and is capable of operating in the recording mode for a period of 30 days with a maximum bottom time of 40 days. The package includes 4 data sensors, 3 seismic and 1 pressure, 4 tri-level reactance amplifiers, a digital clock, and a 14-channel AM magnetic tape recorder. Recall is accomplished either by sonar command from the operations vessel or by internal clock release. Explosives used for experiment calibration are also loaded onto the operations vessel. The bay at Port Angeles, Washington was chosen for an initial shakedown cruise. A unit is launched in 80 feet of water for a 24-hour operational test. The sonar transducer, lowered over the stern of the ship, releases the test unit, which rises quickly to the surface. After unit recovery, the ocean bottom seismograph is returned to the engineering laboratory, where the test tape is removed and played back on shipboard playback equipment. System checks are made on the recovered unit, the silver cell batteries are recharged, and the unit is readied for another launch. The motor vessel Virgo is a 165-foot deep-sea oceanographic vessel of the offshore supply ship type. A broad beam, low center of gravity, and twin screws allow the Virgo to maintain a stable working platform during operations. The ship has quarters for 28 men, 19 scientists, and 9 crew members, and an endurance of from 30 to 50 days. Equipment on the Virgo includes a gyro compass with autopilot, 48-mile range radar, radio telephone and radio direction finder equipment, and a 400-fathom depth recorder. "4,000 square feet of open deck space provides ample room for the engineering laboratory, hydraulic crane, shooter's shack, and 100 tons of explosives. Base of the 1967 Aleutian Islands experiment is Adak, Alaska. We wish to thank the Adak Naval Station, Naval Communications Station, and Alaskan Communications Region for their cooperation and assistance during the field program. We would also like to thank the Air Weather Service for their monitoring and timely reporting of surfaced units. A final shakedown cruise is taken prior to the commencement of field operations. The objective of the cruise is to conduct final checks on navigation and radio direction finding equipment. A test unit without anchor is placed in the water and allowed to float away from the ship. The unit transmitter and beacon light are operating so that both audible and visual methods of unit location can be evaluated. Subsequent maneuvering of the ship around the unit allows checkout tests to be conducted. The ocean bottom seismograph is easily launched off the side of the ship. The 4-foot transmitter antenna is swung down to the side of the unit to eliminate possible ocean current-induced noise on the ocean bottom. A trip release connector is attached between the crane hook and unit bridle sling. Tag lines are run through the side rings to steady the unit. When the unit is in launch position, tag lines are removed. The trip release is pulled, and the ocean bottom seismograph starts its descent to the ocean floor at a rate of approximately 6 feet per second. At the time of launch, both the radio transmitter and beacon light are operating. The transmitter will be turned off by the saltwater short, which is created when the tip of the antenna is submerged in the water, and the beacon light is turned off by a pressure switch, which is activated when the unit reaches a depth of 600 feet below the surface. Both systems will then remain inoperative until the unit is recalled. The ocean bottom seismograph is also equipped with a saltwater release system, which will disengage the anchor from the unit if a leak develops and saltwater collects inside the sphere. A series of 5-ton chemical explosives are detonated after deployment of the ocean bottom seismographs. Charges are pre-packaged in 6 by 6 foot metal cages to facilitate handling and storage. Safety procedures are established and observed by all personnel. The entire explosives program is under the strict supervision of the operations manager and the shooter. Charges are launched off the stern of the ship using the hydraulic crane and an A-frame welded on the swivels to the stern of the vessel. Initial preparation consists of placing a charge on the A-frame with about 1 foot of the cage extending over the stern of the ship. Once in place, the charge is secured by chains connected to pad eyes on the deck, and the harness is tied to the top of the charge cage. The charge is supported in the water by means of a 4 by 4 by 8 foot wooden box buoy filled with styrofoam. A 1 1/2 inch diameter nylon rope, cut to the desired length, is tied between the box buoy and the charge harness. The box buoy is launched over the stern of the ship using the hydraulic crane and the same quick-release connector used to deploy the ocean bottom seismographs. After the box buoy is launched, the ship pulls ahead slowly until the box buoy and charge support rope are floating directly behind the ship. final preparation and launch procedures are then begun. All radar and transmitting equipment is turned off and secured after a radar sweep is made to determine if any ships are in the area. Then the shooter and safety engineer proceed to the explosives magazine and remove the necessary primers, boosters, and caps. The blasting caps are placed in a lead-lined safety box. They are then checked for continuity and connected to the firing line, while the shooter's helper places the boosters and primers into the top of the charge. When all preparations are complete, the blasting caps are inserted into the primers, thus arming the charge. The chains are immediately removed from the charge, and the charge is launched by raising the free end of the A-frame with a hydraulic crane, allowing the charge to slide off the stern into the water. After the charge has been launched, the ship pulls ahead slowly, and the firing line is reeled out. The firing line reel is located on the rear of the ship's stack and is controlled electrically from the shooter's shack. Care is taken to keep the box buoy and charge directly behind the ship. When approximately 3,500 feet of firing line has been reeled out, the ship is stopped. The radar is turned on, and a survey is made to ensure that no ships are in the area. Then, the charge is detonated. After detonation, the firing line is reeled in and the box buoy is retrieved. After retrieval of the box buoy, the charge support rope is pulled in. All equipment on the back deck is secured for travel, and preparations begin for another calibration shot. An important part of the calibration explosion program is the shipboard recording of hydroacoustic data. Detonation times and hydroacoustic arrival time data are recorded both on magnetic tape and paper. The box buoy is launched for another shot. Styrofoam blocks are tied to the charge support cage to slow the descent of the charge after launch. Several hydrophones are used to record the hydroacoustic data. One hydrophone is tied to the bottom of the box buoy to record arrival time data directly above the charge, while the remaining hydrophones are placed off the bow and along the port side of the ship. The ship again pulls ahead slowly until the box buoy and charge support cage are directly behind the ship. Checkout of the hydroacoustic wave recording equipment is completed while the charge is being prepared. The ship's radar is again turned off after a survey is made to determine if any ships are in the area, and the primers, boosters, and caps are removed from the magazine. The shooter and safety engineers again check the caps for continuity and connect the caps to the firing line. After all preparations are complete, the charge is armed and launched off the stern of the ship. While the firing line is being reeled out, final checks are made on the hydroacoustic wave recording equipment. The recording wire connected to the hydrophone on the box buoy is reeled out along with the firing line. When the ship stops for detonation, the shipboard hydrophones are lowered over the side of the ship. After detonation, the firing line is again reeled in, the box buoy and charge support cage are retrieved, and all equipment is resecured for travel. Sonar recall is accomplished using a transducer which is lowered over the stern of the ship to a depth of approximately 15 feet and towed using the hydraulic crane. The sonar signal transmitted by the transducer is received by the ocean bottom seismograph pressure sensor and decoded within the unit. Each system is assigned a unique code, and release can be only initiated by the correct code. Units have been released by sonar recall up to a distance of 14 miles from the ship. The ocean bottom seismograph rises to the surface at a rate of approximately 4 feet per second. The radio transmitter antenna swings into the upright position as the unit surfaces, and the transmitter is activated. The beacon light begins flashing when the unit rises above a depth of 600 feet. The prime location system is the unit's radio transmitter. Radio direction finding equipment on the operations vessel is used to locate the surfaced unit in a minimum of time. Visual sighting is aided by the fluorescent international orange color of the sphere. The powerful flashing beacon light, which can be easily seen up to a distance of 6 miles on a clear night, is useful during night recovery operations. The ship moves alongside the surfaced unit. The crane hook is attached to a boat hook, and a second boat hook is used to pull the unit closer to the ship so that the crane hook may be slipped over the sling. The unit is pulled up by the hydraulic crane and placed on the turntable so that it can be taken into the engineering laboratory. The successful completion of the 1967 Aleutian Islands experiment provides useful ocean bottom data for many seismic studies.